Today we're going to take a look at, and tomorrow, we're going to take a look at right triangles and trig ratios. And this may be a little bit of review for some of you. You may have seen this in Algebra 1. Some of you have already had geometry, so you've been exposed to the trig ratios or trig functions. So it's my goal today to define the 6 trig ratios, or at least show you how they're found. And we're going to use these to solve some problems, as you can see the standard says. Today we're going to focus on finding lengths of the sides, and then tomorrow, part 2, we'll focus on finding measurements of angles in a right triangle. So everything we're doing is based on the right triangle. So first thing we should do is just go ahead and look at the 6 trig ratios, and this is going to be really the backbone of this entire lesson. Your homework is going to be your use of the appropriate trig ratio in order to find a missing side, or sometimes you'll be finding 2 different missing sides. So maybe you're familiar. I went ahead and put in red, as you can see, the first letters of the trig ratio and then the first letters of the actual ratio. And if you take those red letters, it spells out the word SOHCAHTOA, and that's kind of the way a lot of people have learned these. Sine means opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So I'm finding that many people are already familiar with these. Not as many people are familiar with the inverse of these. So if you look at the sine function, if you just take the sine ratio and flip it over, then you have the ratio called cosecant, and it's abbreviated CSC. So the inverse of the cosine ratio or function is called secant, abbreviated SEC. And then this one probably makes sense to most people. The inverse of the tangent function is called cotangent. And do you remember how earlier when we were looking at inverse functions, just by way of review, if we had a function and we wanted to find its inverse, we used that little, looks like a -1 exponent, and it means the inverse of. Well, that's the way this is being used now. Cosecant is the inverse of the sine ratio. Secant is the inverse of cosine. Cotangent is the inverse of tangent. So it's very important, and most people probably get this, but I just wanted to make sure this is foundational to your proper use of the 6 trig ratios, and that is understanding what it means to be a side opposite an angle. And I'm using what most math books do use when they're talking about angles, when we're just letting this refer to any angle. They use the Greek letter theta. So in this case, here we have theta representing this angle. You could have also called it angle A. I just wanted you to be aware of what this means, and you're going to see it later on in this textbook and then future math classes. So what would we say is the side that's opposite to the angle theta? Well, just think of looking straight out from this angle. If this were an eye looking straight out, then the side that's directly across from angle theta has a measurement of 11. The side that's adjacent to theta, adjacent means next to, would be the side that's measured 10.2. The hypotenuse, a lot of different ways of understanding the hypotenuse. The 2 most common is that it is the longest of the 3 sides of a right triangle, and it's also the side that is directly opposite the right angle. So you probably already know that this symbol references that this is C is the right angle. Well, this symbol kind of points to the hypotenuse. Okay, so those are probably the most commonly used ways of recognizing the hypotenuse. So we have the opposite side, the adjacent side, and the hypotenuse. And you can see how all of those come into play in your trig ratios. All right, let's just try this little exercise again. Here's theta. What is the side opposite to theta? That would be the one that has a length of 8. The side adjacent to theta, well, you might say, well, both of these are adjacent. Well, remember, what is the hypotenuse? Well, the hypotenuse is the side, first of all, it's the longest side, and it's also the side across from the right angle. So that means the side adjacent to theta is the one that measures 15. Okay, I think I'll come back later in the lesson and talk about the unit circle, but for now I'll just tell you that right triangle trig really didn't start out as a right triangle. It started out a long time ago, probably in the 2nd or 3rd century, using what is known as the unit circle. And this isn't the whole unit circle, but I want to use it when we get to a particular problem to define the cosine of a particular angle measurement. So I want you to understand why cosine of a particular angle is the number that it is. And I didn't want to just give it to you. I'm hoping to use the unit circle to prove that when we get to that point. So we'll be coming back to this, but for now, let's just get into some of your homework problems for this evening. So what I've done is I just made up my own problem that is very close to your number 1 on page 782. So there's really 2 answers that we're coming up with. So to set this problem up, we've got this hot air balloon. We're told that it's 5,000 feet above the ground. And from this balloon, we see a clearing. All right, so in your book, you'll see trees and all this kind of stuff down here. I didn't bother to put that in. But at this point, you'll see a clearing area, maybe a place for the balloon to land. So they give us, for this particular angle that measures 35 degrees, by the way, this is known as an angle of depression. And I want you to be familiar with that phrase when you see it. If you're standing on a horizontal and a downward look or a downward movement, it's almost like this line has been moved down 35 degrees, and it makes sense that downward would relate to the word depression. So this is an example of an angle of depression. From a horizontal and then looking downward or moving downward from there a certain distance, in this case 35 degrees. Well, its counterpart, if we're standing on a horizontal and we look upward, or maybe it's any kind of upward movement from the horizontal, then this is known as an angle of elevation. Okay, so I just wanted you to be aware, if you've never heard of those phrases before, what they mean. So from the horizontal looking up, angle of elevation, down will be angle of depression. Okay, so all right, so now you're aware, and let's see if we can figure out the answers A and B. So what does this mean? Your horizontal distance from the clearing. So basically, we're talking about this distance, this horizontal line, and I've called it A simply because this is the answer that I'm looking for 1A. All right, and you'll notice I'll do something similar with B when we get to that point. So really, I'm just looking for this side of this triangle. All right, so here's my right angle. Well, thinking back on our trig functions and looking out from the angle that measures 35 degrees, I notice that I'm given the opposite side. I'm not given the adjacent side. Okay, So one of the things we could do, if we look at our trig ratios, we have a ratio that deals with the opposite side being divided by the adjacent side. And if you go back and look at your notes, you'll notice that that is tangent. Tangent is opposite divided by adjacent. Okay? So getting specific, that's what tangent is in general, but applying to this problem, we would say tangent 35 degrees, okay, equals the opposite side length, which is 5,000, divided by the adjacent side length, which is what we're actually looking for. So I'm just going to call this A. All right. Well, fortunately, we don't even have to do this in our calculator because we are given what the decimal equivalent, at least the rounded form, of tangent 35 is. It's 0.70. And I'm just going to go through some algebra here and solve for A. So I'm going to multiply both sides by A. And then, of course, we'll divide by 0.70. And you definitely will use your calculator a lot in this lesson, so let's just go ahead and see if we can come up with 5,000 divided by 0.70, and that's 7142.857, but the directions tell us to round to the nearest foot. So rounding to the nearest foot, we will have 7143. All right, so that's my answer for letter A. 7,143 feet. All right, so now we're ready for part B, and I've just labeled this line, which represents the direct distance from the balloon to the clearing. I labeled it as B because that's my answer that I'm looking for. So again, I'm going to use trig ratios. You might think, well, why don't we use the Pythagorean theorem? That also is very useful in helping us find missing side of a triangle if we know two of the sides. Well, it would work okay, except that these decimals that were given for sine, cosine, and tangent have been rounded, and that really does affect the accuracy of our answer. So we're just going to go ahead and use another trig function. All right, so let's go back to our 35-degree angle. We know we have opposite, and now we're looking for hypotenuse. Okay, so look at your trig functions. Eventually you'll do this so much and you'll have these committed to memory so that you'll just know that the ratio that for an angle that involves opposite over hypotenuse is sine. Okay, I'm just writing these out so you'll just see them again, get used to seeing these ratios. It's going to be your job to have these committed to memory. So once again, in this case, getting specific to this problem, sine 35 degrees is equal to 5,000, the opposite side, divided by the hypotenuse, which is what we're actually looking for. Well, sine 35 degrees has been given 0.57. So I'm going to solve for B, multiply by B on both sides. 0.57B is 5,000. And if I divide 5,000 by 0.57, I will have 8771.929. But again, we're rounding to the nearest foot, so 8772 feet. So that's my answer for letter B. Okay, and that completes problem number 1. You're going to do a problem very, very much like it. So I hope this problem helps you when you get ready to do homework number 1. Okay, well, let's take a look at a problem very much like number 2 on this same page. They're going to give you a triangle, and I've pretty much reproduced that triangle, but I'm using different side measurements. And it's our job to run through these indicated trig functions. Okay, so let's start off with letter A. It says sine A. Well, here's the angle A looking out from angle A. Remember, sine is opposite over hypotenuse. The opposite side for A is 12. The hypotenuse, of course, is the side opposite the right angle, which is 13. All right, and so notice the directions say to write each value as a fraction. We just did that. And as a decimal rounded to the nearest hundredth. So I'm not going to do all of these because I'm sure that you can take care of changing the fraction into decimal, but for this one we'll do it. And so my final answer for letter A, fraction form and then decimal form. Okay, still looking out from angle A, I'm asked to find secant A. Well, remember, secant is the inverse of cosine. Cosine is adjacent over hypotenuse, which means that secant, if it's the inverse, is just this ratio flipped over. So it's going to be hypotenuse over adjacent. All right. I just want you to see these inverses of the three main trig functions that you're probably already familiar with. All right. So secant is hypotenuse over adjacent. And so looking out from angle A, the hypotenuse is 13. And the side that's adjacent to angle A is this side AC, which measures 5. And then don't forget to give me the decimal form of that. All right, let's move along. Cotangent A. Well, cotangent A is the inverse of tangent A. And tangent is opposite over adjacent. So cotangent would just be that ratio flipped over. It's adjacent over opposite. Okay, and for A, adjacent is 5, opposite is 12, and then don't forget to come up with the decimal form of that. Cosecant B. Well, cosecant is the inverse of sine. Sine is opposite over hypotenuse. So for cosecant, we will just flip it over. Hypotenuse over opposite. And now notice our angle has changed. We're now looking out from angle B. So if we do hypotenuse, which is still 13, over opposite, we get 13 over 5, and then the decimal form. All right. Secant. Remember, secant is hypotenuse over adjacent. And now we're going to do that for angle B. All right, so for angle B, the hypotenuse again is 13. The adjacent side for angle B is 12. And then the decimal form. And then we got one more for this homework problem, tangent B. Remember, tangent is opposite over adjacent. So in this case, for angle B, the opposite is 5, and the adjacent is 12, and then come up with the decimal form. All right, just practicing the trig functions for number 2. Okay, this problem's similar. It's just that we're going to have to draw our own triangle. So let's draw this right triangle. And we're told that H is the right angle, so we can call this G and this I. Let's see what else we're told. The leg known as GH is measured at 29. And we're also told that cosine G, okay, here's G, is the ratio 29 over 30. Well, again, remember cosine is adjacent over hypotenuse. Well, the adjacent side was given to us, and by giving us this ratio, they're basically telling us that the hypotenuse measures 30. So it's going to be our job to find out the length of this leg known as HI. Well, we're going to rely on the Pythagorean theorem. So the Pythagorean theorem will help us find the measurement of this leg known as HI. So c squared, here's a Pythagorean theorem in case you forgot, 30 squared, c is the hypotenuse, equals one of the legs squared plus the other leg squared. So in your calculator you could just do this, 30 squared minus 29 squared. So let's see what that is. 30 squared minus 29 squared. That equals 59, and then we need to do the square root of that to come up with actual b. Remember, that represents b squared. And it's in a decimal, 7.6811. I'm just going to round to the nearest whole number. I'm going to say that this is 8. Okay. And it's an approximation. All right. Okay, so now we are ready to come up with these ratios. So here we are looking out from angle G, and I'm supposed to find sine G, and that is opposite over hypotenuse, 8 over 30, and I always like to reduce, so we can do 4/15, and then once again you're doing the fraction and the decimal form, so I won't take the time. I'm sure you know how to do this, and you can go ahead like the previous set of problems and round to the nearest hundredth, I believe. Yeah. All right, let's take a look at sine I. All right, we're looking out from angle I this time. Again, sine is opposite over hypotenuse. So that's 29 over 30, and then the decimal form. Okay, cotangent G. Well, if it helps, just think about tangent G. Most people are familiar with sine, cosine, and tangent. Tangent G is opposite over adjacent. Well, cotangent is just the inverse of that. It's adjacent over opposite. Okay, so looking out from G, the adjacent side is 29, and the opposite side is 8. And then you would find the decimal form. Okay, cosecant G. Well, cosecant is the inverse of sine. It's the same thing as this. Okay, well, sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. Okay, so for angle G, hypotenuse is 30. The opposite side to angle G is 8. And then we will reduce. And you could have just taken the result from sine G and letter A and flipped it over, because again, cosecant is inverse sine. Okay, let's do cosine I. All right, cosine, remember, is adjacent over hypotenuse. For angle I, adjacent means 8. Hypotenuse is 30. Reduce 4/15. I forgot. Don't forget to do decimals. Okay, so now we get to letter F, and we're asked to do secant of this right angle on this H. And this is where I want to go back, and we'll come back and answer this, but I could just tell you that cosine of a right angle is 0, but I wanted to show you using the unit circle, and you're going to study the unit circle in depth in future math classes like Algebra 3, Pre-Calculus, Calculus. And this isn't the entire unit circle, but it's just enough for me to help illustrate some of these truths about 90 degrees. Think of this angle theta as a line that starts here on the x-axis and then just rotates counterclockwise along this circle. Okay, and your trig ratios, as you can see, sine of theta on this unit circle is the y-coordinate over r, the radius, and cosine theta would be the x-coordinate over the radius. Okay, it's just another way of showing those same ratios. If you think about it, here's theta. We've been thinking of sine as opposite over hypotenuse, and that's exactly the way it is, showing these variables. Cosine is adjacent over hypotenuse. Okay, so really the trig functions are related to this ordered pair of this point on the circle, and as this angle rotates around, that's going to change the value of my trig functions. Well, notice when this angle becomes here, 90 degrees. Okay, well, obviously at this point on my circle, the x-coordinate is 0 and the y-coordinate of this point is 1. So if I use this same line of thinking of cosine is the x-coordinate divided by the radius, well, the x-coordinate at this point is 0, and it really doesn't matter what the radius is. 0 divided by anything is still 0. So that helps us prove a little bit that cosine of 90 degrees is 0. All right, so and along the same lines, you can see that with the y-coordinate being 1 in this ordered pair that is now shifted over here, and if we find sine by doing the y-coordinate divided by radius, well, this radius is 1. 1 divided by 1 is 1. Okay, so sine 90 degrees is 1. Cosine 90 degrees is 0. Notice tangent 90 degrees. Well, tangent is opposite over adjacent. Well, at this point, we're doing y divided by x. At this point, y is 1 and x is 0. Well, we know from past studies that we can't divide by 0. So tangent 90 degrees is actually undefined. Okay. Secant 90 degrees. Well, remember, secant is inverse cosine. All right, so if I want to know secant 90 degrees, I'll take cosine 90 degrees, which is 0 over 1, and flip it over. Well, once again, very much like with tangent 90 degrees, I have something that is undefined. All right, so that's kind of the short version behind getting to the answer here. Here I'm asked to find secant of h, which is another way of saying, since h is a 90 degree angle, what is secant 90 degrees? And I hope, even though it's a quick proof, I hope that you understand now that secant 90 degrees is actually not even defined. So my answer for letter F, and your homework will be very much like this, is undefined. Okay, that takes care of number 3. Number 4. Okay, once again, we're supposed to draw a triangle, so let's do that first. Here's my right triangle. This time, R is the right angle, and so we'll just let this be P and this be Q. This time we're told that the angle P, cotangent P, is 5/9. Well, that tells me that tangent P, which is the inverse of this, is 9/5. Okay, so right away I've got one of my answers. And of course, again, you got to do the decimal, so don't forget that. What do we know about tangent? Well, the ratio of tangent is opposite over adjacent. So in relation to P, the opposite side will be 9, and the adjacent side will be 5. All right? So now how do I find this hypotenuse? Well, I'm going to go to the Pythagorean theorem. C squared, C stands for the hypotenuse, equals, really doesn't matter which one of these you call A and B, A squared plus B squared. All right, so we get 25 plus 81. That's 106. Don't forget we need C, not C squared. So the square root of that will be, it's 10.29563014. So once again, I'm just going to round to the nearest whole number. You won't have to worry about this on your homework, coming up with a decimal. So we'll just, for practice sake, we'll just say that this is 10. Okay, well now we have the sides, we can come up with these trig ratios. So sine P, all right, looking out from P, sine is opposite over hypotenuse. Okay, opposite over hypotenuse. So sine P is 9/10, or in decimal form, we'd say that's 0.9. All right, cosine P. Cosine is adjacent, which in this case is 5, over hypotenuse, 5/10. That's easy enough, which is 0.5. And then we've already found tangent P because we were given cotangent P, so you'll need to come up with the decimal there. Cosecant, well remember cosecant is inverse sine, so if sine is 9/10, then cosecant is 10/9. And remember that secant is inverse cosine. So if cosine was 5/10, then secant P would be 10/5, which is 2. And your number 4 will look a lot like this. Okay, well, I only have these 3 examples, and I'm going to let you see what you can come up with on number 8, A, B, and C. I think after you've done these examples 1 through 7, I don't think you'll have any trouble coming up with the answers to the flagpole problem. So let's go ahead and finish this off. Your number 5 looks a lot like this one. We're supposed to find the indicated length. So in this case, we're trying to find the hypotenuse. Well, let's see what we're given. Relative to this angle measured 32 degrees, I'm given the adjacent side. Okay, and I'm looking for the hypotenuse. So think about the trig ratio that involves adjacent hypotenuse, and hopefully you came up with cosine. So cosine 32 is equal to adjacent over the hypotenuse, which is what we're trying to find. It's unknown at this point. Okay, so I'm trying to solve for x, and solving for x algebraically, it would look like this. I just multiplied by x on both sides, and now I'm going to divide by cosine 32 on both sides. And I would literally enter it into your calculator like this. If you do 17 divided by and then cosine 32, you end up with 20.0460326. We're rounding to the nearest tenth, so that would actually be 20.0 to the nearest tenth. All right, so that would be my answer for number 5. Let's take a look at number 6. This time I've got this angle measured 24 degrees. I know the side opposite to that. I'm looking for the side adjacent to that. So let's think of the trig ratio that would provide me with opposite over adjacent. And hopefully, if you had to look back on your notes, you discover that that is tangent. Okay? Tangent 24 degrees. And so in your calculator, you're just going to do tangent 24 equals the opposite side, which is 13, divided by the adjacent side, which is x, unknown at this point. So multiply by x on both sides. And this one's very similar to our other one. This time we're going to, in our calculator, we're going to do 13 divided by tangent, and then in parentheses we'll put 24. And to the nearest tenth, the decimal reads 29.19847. To the nearest tenth, that's 29.2. So that's my answer for number 6. And then finally, number 7, this will be my last example. Thank you for hanging in there. Here we have this angle, and I'm trying to find the hypotenuse. Well, think of the ratio that involves opposite and hypotenuse. Okay, and hopefully you remember that that's sine. Sine is opposite over hypotenuse. So we're going to do sine 41 equals the opposite side, which is 5.7, divided by the unknown hypotenuse. Okay, solving for x, x times sine 41 equals 5.7, dividing by sine 41. So in your calculator, I would key it in like this, 5.7 divided by sine, and then in parentheses 41. And you should come up with 8.68824 and so on, but to the nearest tenth, that should be 8.7. Okay, well that does it. And then once again, you've got one more problem, number 8, but I think you've seen enough to where you should be able to handle parts 8, A, B, and C. So that's your overall assignment. I hope you do well with it, and I'm open for questions. You can email me, come in for academic support, and we'll see how you did tomorrow.